Yes, so for example, transfer money from one account to another account, or book a flight, or find a restaurant. So these tasks are called, or these dialogue systems are called limited domain dialogue systems. So there is a predefined set of things that they could do or they can talk about. And there are lots of such applications. The second group of dialogue systems are open domain dialogue systems, to which you can talk about anything. And these are very challenging to solve. And currently, they only exist on the level of chatbots. So they sort of pretend to be human-like, but they actually have, they only imitate the way users speak. They're not they cannot converse with you intelligently. So in this talk, I'm going to focus on limited domain dialogue systems, and within this group on systems which are goal-directed. So where user has a clear goal in mind that they want to fulfill. So find a restaurant, book a particular flight, make a transaction, and so on. So to give you an idea of how would we like these systems to be, I'm going to play a little video which might be familiar to some of you.
Read me the message.
New message from Sebastian. Great news. We got the go-ahead. Can you meet at 10?
Reply, definitely. I'll see you there. Play my running mix.
What's the traffic like around here?
Here's the traffic.
Text my wife, I'm going to be 30 minutes late.
Is it going to be chilly in San Francisco this weekend?
Not too cold. Maybe down to 61 degrees in San Francisco.
What about Napa Valley?
Doesn't seem like it.
How many cups are in 12 ounces?
Let me think.
So you get the idea.
Okay, here you go.
Just for curiosity, how many of you have actually tried Siri or Google Now? Okay. Any of you using it on a daily basis? No. Why? Well, because you'll find out that the reality is more like this.
What's the buttons?
Oh no, they installed voice recognition technology in this lift. I heard about this.
Voice recognition technology? In a lift? In Scotland? You ever tried voice recognition technology?
No.
They don't do Scottish accents.
11.
Could you please repeat that?
11.
11. 11.
11.
Could you please repeat that?
11.
Whose idea was this? You need to try an American accent.
11. 11. 11.
Where in America is that? Dublin?
I'm sorry. Could you please repeat that?
Try an English accent, right?
11. 11.
You for the same part of England as Dick Van Dyke?
Listen, you're then smart ass.
Okay,
Please speak slowly and clearly.
Okay, so what we know about spoken dialogue systems is that primary input is speech. They have innumerable benefits. There are lots of applications that we can use them for, but building them to operate robustly is challenging. Now, I'm going to ask you, if you didn't hear the talk this morning, how would you build a spoken dialogue system? What would you start with? Any ideas? Yes?
Noise robust.
Okay. And then, once you get the input from speech recognizer, what would you do? And then you would propose what to say to the user. Okay, that's similar to how people used to build these systems. So you start by asking user a question. Say, if you're building a tourist information system, are you looking for a hotel or a restaurant? And then you have the user. You recognize user speech. So the user may say a restaurant or a hotel. And then in the case of restaurant, you ask, what kind of food would you like? In the case of hotel, you ask how many stars. And then you may ask which part of town, and so on. So let's see now what happens in one of the nodes. So this is called the call flow. This is how the conversation grows over time. Let's see what happens in one of the nodes of this tree. For example, which food? So you ask the question, and that gets generated into speech. And then you have the user, which says something back. Now, because you asked the user a question, say, what was the question? What kind of food would you like? You expect a certain answer to be in a certain form. So you know user will talk about cuisine. So user may say, I want Indian food, or I want Italian food. So then you load the grammar into the speech recognizer to be able to recognize user speech. And usually these systems associate a confidence score to their output. So the confidence score measures how confident the system is in its own output. And you can use that in the following way. So if the confidence score is very high, if the confidence score is high, you go on to ask the next question. If the confidence score is medium, you can say, sorry, did you say want Indian food? And then if the user says no, you ask the question again. If the user says yes, you go on to the next question. And if the confidence score is low, you repeat the question again. Now, does anyone see problem with this approach? Yes?
Hey, this kind of directed dialogue, it's a bit annoying for a user because there are multiple steps and it's not natural. Another problem is that you should take the confidence score after a confirmation. In this flow, also.
So you first get the confidence score, and then you decide whether you want to confirm.
Okay, I didn't see the arrow. Okay.
Any other problem? Yes?
It may happen.
Oh, yes, exactly. That's the biggest problem here. Because if the confidence score is low, you ask the question again, but you ask the same question. You load the same grammar, the user repeats the same thing again in the same way, and you get the same confidence score again. And then you enter in endless loop. So that is one problem with traditional approach to dialogue systems. The other problem is that these systems are extremely laborious to build. So this is call flow, a part of call flow, of a real deployed dialogue system. So for each of these boxes, someone had to sit down, devise a set of rules, write them out, write an error handler to each of these boxes, because the system can break at any time, and then deploy them for a particular task. Now, if you want to use it for another task, you have to start from scratch. There is no way to transfer from one task to another. And also, these systems, once they get deployed, they serve thousands of dialogues every day. And they are making the same mistake over and over again. And they have no way of improving automatically, which is a huge pity because they generate a huge amount of data. It can only be improved if someone actually says, okay, it makes a mistake there, I'm going to go and manually fix them. So major limitations of this approach is that it's extremely expensive to be built. It's fragile to speech recognition errors. And does it improve with the time of use? Well, no, unless someone manually fixes them. So, in order to deal with all these problems, people have proposed a statistical approach to dialogue modeling. And the first step in this approach is to decompose the problem into smaller problems. So now, statistical spoken dialogue system consists of separate modules. So the first module is speech recognition, which simply recognizes what the user is saying, independently of where in dialogue we are. Say, I'm looking for a restaurant. Then the second part is called semantic decoding, which now tries to look for the meaning in what the user is saying. So there are many ways you can say I'm looking for a restaurant, but it actually all means the same thing. So there is some high-level representation of that, in this case, inform type equals restaurant. And then you have the dialogue manager. Dialogue manager now decides what to say back to the user. For example, request food. This gets passed to the natural language generator, which generates this into text. Say, what kind of food would you like? Finally, this gets passed to text-to-speech synthesizer, which synthesizes this into speech. Now, for each of these modules, we have a well-defined input and output, which means that we can, with enough training data, we can train each of these modules in a statistical way. So, what are statistical methods? Human data exhibits some events that are usually non-deterministic. So we want to model that with probability distributions. This would allow us then to make predictions, to behave like a human does. Why do we want to do that? Well, we want to learn from data because it has benefits that we don't need then to handcraft the behavior. It can be more natural, and most importantly, it can improve with the time of use. So now I'm going to pause there and give you a bit of theory. How many of you have heard of Bayesian networks? Okay. So Bayesian networks allow us to specify relationships between random variables. So in other way, a random variable can take some values, and another the values that a random variable can take can be influenced by probability distribution of another variable. So here we have a direct acyclic graph between three variables. The nodes are random variables, and these are the events or behavior that we want to model. And these arrows represent relationship between them. So it allows us to estimate joint probability distribution. And it factorizes the product of nodes given its parents. So in this case, we have probability of A, B, and C is factored as probability of A, probability of B given A, and probability of C given A. So you can see from here that B only depends on A. It doesn't depend on C. So this arrow corresponds to that probability distribution, and this other arrow to the probability of C given A. Now, if we have the graph, probability of A and B is the probability of A, B, and C when we marginalize all of C's. But then from here, and looking at this graph, we can see that this is the same as probability of A times probability of B times probability of C given A and B. But now these two guys don't depend on C, so they can go outside of sum. And when we sum the last element out, we get the probability of A and B. So this means that if C is not observed, A and B are independent. So Bayesian network allow us to incorporate useful independence properties. Now, what happens if a variable is observed? So colored nodes represent events that we observe. So now we know that A took some value. And we want to know what is the probability of B and C given A. Now, that is the probability of A, B, and C given divided by probability of A. But probability of A, B, and C from this graph is factored as probability of A times probability of B given A times probability of C given A divided with probability of A, which then results into probability of B given A and probability of C given A, which means that B and C are conditionally independent given A. So if we know the value of A, these two variables are independent. Okay, so that was the theory. Let's go back to the statistical spoken dialogue system structure. Now, as I said, each of these methods can be built using statistical methods, and I'm just very briefly going to talk about each of them. So the first is speech recognition. So many of you know that when we have speech, we can extract some features. And these are just numbers corresponding to the speech. But there is not one-to-one mapping between the numbers and the actual words that the person is saying. So what people use is a hidden Markov model to model the relationship between these observations and the elements that phones or words. So the element that we want to estimate is, say, a phone or part of the phone, and it's an unobservable random variable. And what makes this model Markov model is that the next variable depends on the previous variable. Also, each of these states, so state is unobservable, and each of these states generates a noisy observation. And this is our MFCC feature. So now you have a graphical model where the probabilities between states are governed with the transition probability, and the probability of observation given state is the observation probability. Now, if you do speech recognition, the transition probabilities will correspond to the transitions between phones. Transitions between words are modeled with a language model. Observation probabilities represent the acoustic model. And the output of speech recognition is an M-best list of possible utterances. And that then gets passed to the second element, which is semantic decoding. So now, semantic decoder tries to find out some high-level representation that represent the meaning of the user utterance. So map this into this. So we are not interested in the exact meaning, just the main concepts. And semantic decoder transcribed each hypothesis from the M-best list. So if you said, for example, there is a cheap place in the center of town, please, that is inform price cheap, area center. So this representation is very common in dialogue systems. It consists of two parts. The first part is dialogue act type, and it entails what is the overall intention that the user had in mind with the whole utterance. These are slots and values, so very common in slot-filling dialogues, and they only refer to parts of utterance. So here, a cheap place means the price is cheap, area center in the center of town. So we have one input, one output, and we can model this with, yes?
Far from the center, and then
yes. So it depends on the features that you use. So normally you extract features from this utterance. And do I have that slide? No. So a very common way to do this is to use unigram, bigrams, or trigrams. So this utterance would have, all of these words would be unigrams, and then for each, you have a huge vector, you fill it with ones and zeros depending which unigram, bigram, or trigram appears. And then hopefully, if you said far from the center, that will trigger, that will be another feature. So the system should learn that that is far from the center or not center. But obviously, there are more sophisticated models that you can use in semantic decoding. And now we come to the third part, which is Dialogue Manager, which now takes as input the semantic output and tries to find appropriate answer to question for the user. Now, can anyone tell me what is the crucial difference between Dialogue Manager and, say, speech recognizer or semantic decoder? Any ideas? Can we decide to ask about food only based on this? Because here, we only need this input to figure out that the user wants a restaurant. For the speech, we only look at that piece of speech to find out that the user said, I'm looking for a restaurant. what happens in the dialog manager? Any ideas? So the dialog manager needs to know the whole history, because it could be the case that the user said already what kind of food they want. Or at this point, you may have a choice of asking about food or asking about the location. But if you already know that the user is looking for something in the center, then you shouldn't be asking about location. So while all other modules are strictly supervised, can be modeled with supervised learning, where you have one input, one output. For dialog manager, you need something that looks back into history. The way it does that is by having two modules. The first module is called dialog model, which keeps track of what has happened during the dialogue. And the second module is called dialog policy, which now decides what to say to the user. So the dialog model keeps track of what state the system is in. Similar as in speech recognition, where you have hidden Markov model, you have some states. But the difference now, and obviously the question is how we represent the state. But the difference is now that you have a dialog policy which models which actions the system should take in each of these states. And then the question is, how do we represent the system action? So a convenient model for dialogue, which incorporates these elements, is called Markov decision process. So dialogue is a sequence of turns. So the system says something, the user says something, and so on. And that is modeled by a state. And then what system says back to the user is modeled by an action and governed by a policy. Then you have the next state. And the next state only depends on the previous state and the action that's taken. Now, you may have, at every time step, some measure of how good it is to take this action in this particular state. And this is Markov decision process. Now, the aim is, as we heard this morning, to take actions in such a way that we get the highest possible reward. The problem, however, with this model is that you are never really certain in which state you are, because speech recognition can make errors. So the way to model this better is to use a partially observable Markov decision process, where state is unobservable, but instead it generates a noisy observation. So now, if you concentrate on this part, and you'll see that this is very similar to hidden Markov model. You have some observations, and you have some hidden states. Only that in this case, the observation is the m-best list that you get from semantic decoder, and the state is some hidden representation of what user wants. What makes this a decision process is the fact that you're making some decisions, you're taking actions, and you may get some observation in terms of a reward of how good your action is. Now, dialog policy in a POMDP is not based on a particular state, but rather on distribution of all possible states. So you can, if you had 3 states in an MDP, in POMDP, your policy will be based on a vector that's three-dimensional, where each dimension corresponds to a particular state and takes values between 0 and 1. So you can see that even for a very simple model, how the problem grows. But I'll talk about dialogue modeling in the second half. Now, let's go back to the original diagram. And let's assume that we somehow found that in this case, the system should ask for food. How do we get from here to here? So what people tend to do is actually use templates. So if you want to inform about, if your action is inform about this name in this particular area, then you can simply replace X with the particular name and Y with the particular area. So, for example, inform name equals Char Su, area equals center is Char Su is in the center of town. But using statistical methods is also possible. And again, you can use supervised learning because your input, you have one input, which is this, and you try to produce one output. So one, I guess, interesting work was using, again, Bayesian networks, where you have hidden representation and some observations, but you actually this time try to generate the observations because you know in which state you are. And final element is text-to-speech synthesizer. So what you can do is record lots and lots of speech samples, cut them, and then stitch them together and then do some post-processing. But you can also use the same model as you use for speech recognition, a hidden Markov model. So in hidden Markov model, you try to infer the state. Here again, you know the state, and you generate the observations. So that is using HMMs for synthesis. So in summary, we talked about spoken dialogue systems. We noted what are the challenges. So if you want to build a spoken dialogue system traditionally, you have to use lots of hand-coded rules, which is very laborious and expensive. It is fragile to speech recognition errors because it doesn't have a good way of dealing with uncertainty, and it doesn't improve with the time of use. So in order to deal with that, we propose statistical dialogue systems that decompose a dialogue system into 5 modules. And for each of these modules, if you have data, you can build them using statistical methods. So this would be my first talk. I would like to take any questions if you have now, then make a break, and then move to the next. Any questions?
Where the states are observations. Like there are some states, however, that like and while some other states.
Well, that would mean that you have probability 1
yes,
for that
states.
state,
yes.
and 0 for all others.
Yeah. So that means
yes, 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 yes. Any more questions? Yes? So that is the job of the semantic decoder. So you have, for usually, someone sits down, looks at the input, the text, and transcribes it. Says, if user said, I'm looking for a restaurant, that means inform type equals restaurant. You gather lots of this data, and then you try to train the model so that when you get an unknown utterance, you can predict what the output is. But also, if you're interested in spoken dialogue systems, I'd suggest first try to build hand code, like semantic parser. You can use Phoenix, and you can write Phoenix grammar. And it's basically a keyword spotter. So you can you can specify, for restaurants, people tend to say restaurant, place to eat, cafe, and so on. So you write all these possibilities. And then when you get an utterance, it basically tries to match what you said. And we normally do that when we want to gather data easily. Okay, so in the first talk, we talked about statistical spoken dialogue systems. And now we are going to focus on dialogue modeling. But let's remind ourselves why are current methods so poor.
Right, look at this, look at this. Radio.
Radio.
FM.
FM. Frequency, please.
85.0.
Sorry.
85.0.
Sorry.
85.0.
Sorry.
85.0.
Sorry.
85.0.
Frequency, please.
85.0.
Sorry.
You stupid woman.
Okay. So the current systems keep asking the same question all over again. And you want to deal with this by having a more sophisticated dialogue manager that can take input from the semantic decoder, produce output, and have an internal model of dialogue and representation of what to do in each dialogue situation. Dialogue model models what the user wants. Dialogue policy models what to say back to the user. Now, elements of dialogue management are observations. So this is what the user hears, because we know that the user cannot hear perfectly what the system, the system cannot hear perfectly what the user is saying. So at every turn of dialogue, we get an observation from the semantic decoder. Now, what we want is for the system to take actions. So that is what system says back to the user in every dialogue turn. And in order to go from here to here, we need to have some internal representation. These are called dialogue states. So that is what the user wants. Now, these are all random variables. These are observable. these we choose. These we can decide whether they are observable or not observable, depending how we model dialogue. Also, what relationships we put between these variables determines which model we use for the dialogue. Now, I'm going to explain this through an example. And I'm going to start with a commercial system. So say this user says, I'm looking for a Thai restaurant. So this is what user says. What system hears is actually more something like this. So I can be recognized as hi, and then interpreted as hello. You may, Thai can be interpreted, heard as hi and interpreted as hello. Then you have restaurant and an associated confidence score. Or you might have perfect recognition. I'm looking for a Thai restaurant. But because you had this one erroneous, this can only have 0.4 confidence score. Now, from here, what commercial systems do, they only look at the top hypotheses. So in this case, you had hello, type equal restaurant. Hello doesn't really mean much, so you are only looking for this dialogue state. You're only interested in type and food, for example. And because here you have 0.6, you have 0.6 as well here. And now 0.6 is relatively low, so a designer may say, no, you really need to confirm this. So the action could be you're looking for a restaurant, right? But the users don't normally tend to follow, to always answer what the system has asked. So the user may just decide to say Thai. Now that can again be recognized as hi and interpreted as hello with 0.5 probability. Or maybe food equals Turkish with 0.6 probability. Or finally as food equals Thai as 0.2. But as I said, these systems normally look at only top hypotheses. So this we only have hello, which doesn't actually bring us any additional information. So these systems only have a memory of what happened before. So you have the same input, which is type restaurant with 0.6 probability, and you ask the same question again. Now, what you want is to exploit the whole MBEST list. And this will be baseline tracker in the practical session. So this now dialogue modeling technique looks at the whole list. So you had type equals restaurant here with 0.6 probability. You also have it here with 0.4 probability, which means that you actually know that user wants restaurant with 1 probability. And from here, you know that user wants Thai with 0.4 probability. So now you don't have to bother about asking whether user wants the restaurant, but you can simply concentrate on food. Now, 0.4 is very low, so you may decide to just ask the user what the user wants. So what kind of food do you want? Now, user says Thai. You get the same MBEST input. You don't know anything about type from this input, but you know about it from the previous turn, so you just keep that information. And now you look at food. So food here is Turkish with 0.3 and Thai with 0.2. So you have two options here. And this tracker only looks at the one which has the highest probability. So Turkish has a higher probability than Thai. So you say user wants Turkish food with 0.3. And then, but this is again very low. And you may ask, what kind of food do you want? Again. So does anyone see how can we improve this? Or if there could be a better way of doing this? Yes?
Maybe.
Yes, but that would be a hand-coded rule, right? Uh-huh.
Go down.
Yes, but you also want to keep the information from the top hypothesis as well. Yes? Yes. So you can take both options, but actually what's more important is to keep track. I said before, we are not only interested in what the user says at this particular turn, we're interested about everything that happened before. So user said tie here with 0.4 probability. User said tie here with 0.2 probability. So actually, when you take both of these probabilities into account, you'll figure out that it's more likely that user wants Thai than Turkish. So the aim of dialogue state tracker is to accumulate these probabilities over time so that nothing is thrown away. So even if you took on both Turkish and Thai from this input, you'll have that Thai is lower probability than Turkish. But if you took into account Thai from this input and Thai from this input, then it will have higher probability than Turkish. And that will be the focus tracker in the practical session. So that is something that you will have to implement. So I will give you the formula, but it will actually come down to be something like you'll have food Thai with 0.4 probability and food Turkish with 0.3 probability. Now you have two competing options, and good thing to do in that case is to say, did you want Thai or Turkish? So you can see that by having a more sophisticated belief tracker or a dialogue state tracker, you actually add more variability in your system's response. Now, challenges in dialogue management are how to define the state space. We saw that we have observations and we have actions. The observation state is huge, so we want to sort of have a minimal state representation, but we want to have to be able to take good actions. The second problem is, how do you calculate these probabilities? So which model do you use to enable you to accurately track the belief state or the dialogue state? And finally, which actions do you take? Now, let's start with the first problem. How to represent the dialogue state. Now, we talked about Markov models, so partially observable Markov decision process or only Markov decision process. And in both of them, the state depends only on the previous state. So that means that the state has to encode enough information so that the next state only depends on what the user said previously, or what happened previously. That means that the state needs to incorporate some form of dialogue history. And dialogue history can be huge, but you have to find out what is important for the conversation. So that is to maintain Markov property. Second element is that we want to model task-oriented dialogues. So that means that the user has a goal in mind, but we may not be sure what this goal is. But we need to track this goal from state to state. So the state needs to incorporate what the user wants. Finally, and most importantly, a dialogue manager has to be robust to errors. And in order to be robust to errors, in each state we need to know what user says. And but we may not know what user says, so we'll keep distribution over possible states, and that would be the user action. Now, when you build statistical dialogue systems, you need to define the scope of the system. And the scope is governed by the ontology. So that defines possible states of user goals. So this is what the system can talk about. This is an example of tourist information ontology. So in this system, the user can talk about restaurants and hotels. Restaurants can have properties like area or food. Area could be north and south. Food can be Chinese or Indian. Hotel can have stars. So this can be very large potentially, but it defines possible elements of user goals. Now, for the practical session, we will have somewhat simpler dialogue state, which is again tourist information state, and it will consist of 3 parts. So the first part defines the user goal. So it has slots, and each slot can have possible values. So in this case, food is British with probability 1, so we don't have any other values. But you can imagine another state could be food is Italian with 0.6 or Indian with 0.4. Now, area could be north, south, east, or west, or could simply be don't care, meaning that the user doesn't care about that value of that particular element. So the system can offer a restaurant anywhere in this town. So that is one element, and this is extracted directly from the ontology. Now, the second element of the state is method. And this is in a way related to user act. So we don't keep exactly what the user said with some probabilities, because that would make dialogue state huge. But we only look at the things which are important. And in this case, it is important how user informed the system about their request. So for example, if the user said, I'm looking for British food and I don't care about area, that means that user gave some constraints to the system. And then the method is by constraint. If the user said, I'm looking for a phone number of Irina Taverna, that means that the user has given a particular name to the system, and then they want to find something else about that system. So then the method would be by name, and so on. Then the third element is requested slots. So in tourist information dialogue system, you may want to find a particular entity or a restaurant, but then you want to know more about that particular entity. So you may like to know what price range this restaurant is in, or what's the phone number. And that is the third element of the dialogue state. Now, let's move to the second problem, which is how do you maintain the distribution over possible dialogue states? So this is normally called the belief state. And instead of P, we write it as SB here. Now, there are two ways that you can model this probability distribution. And the first way is using discriminative model. So that means that the state depends on the observation. And if you represent that with a graphical model, you have an arrow going from observation to state. And you can write that as probability of state given the observation. This is also very common in, as this can be seen basically as a function where you give it observation and it produces the state as the output or the distribution over possible states. Another way to look at the problem is to take generative model in which the state generates the observation. So this is now more similar to the hidden Markov model, where you have state, and then from the state the arrow goes to observation. Now the belief state is the joint probability of state and observation divided with the probability of observation, where you now marginalize out all possible states, and you get only probability of observation. But this can be considered as a constant because it doesn't depend on the state. So then it's proportional to probability of observation given state times probability of state. So now the difference here is that the state determines observation. And this is now, if you model this probability, it's a generative model. Now, for the practical that we'll have this afternoon, you're going to implement a discriminative model, which is called Focus Dialog State Tracker. And it's actually a very simple but very powerful model. It tells you that belief of a state taking a particular value S is whatever we got from the semantic decoder for that particular value. So in the case where we had Turkish, it would be whatever the SLU said for Turkish. But now, in order to incorporate what happened before, you will say if there is any remaining probability for that particular for that particular concept. So if we in our case we had Turkish and Thai, and one was 0.2, the other one was 0.3. So 0.5 was not assigned to anything. Now, 1 minus that value, in this case 0.5, we will look at the previous term and take into account that probability. So now, in order for this to be probability distribution, this has to sum up to 1 for every state. So if you put a sum over here, you'll get a sum over all probability over all inputs, 1 minus the same sum times this, and you will figure if you do the math, you'll see that it's equal to just sum over this part. But because if this is probability distribution, then this will be probability distribution as well. So it's fine to use this model. But we will talk more about this model in the practical session. Now, the most famous example of a generative model is partially observable Markov decision process. And as we saw before, state is not observable, and it generates noisy observation. Now, I'm going to make a break there and tell you a little bit about belief propagation. Unobservable variables are dependent on observation. And they can either be dependent on an observation, which we call data, that is what we see, or they can generate some observation against some other data. What we are interested in is the marginal probability. That will give us the belief state. So in this case, we are interested in probability of x given these two observations. Now, probability of x given dB and dA is proportional to probability of x and dB given dA, because we can assume that the probability of dB is only a constant. Now, this can be rewritten as probability of dB given x dA times probability of x given dA. Now, because we have a graphical model here, we can see that dB given x doesn't actually depend on dA anymore. So this is now dB given x times dx times probability of x given dA. Here. So if you want to find marginal probability of x, calculate the probability of everything that goes into x times the probability of everything that goes out from x. But it can be a little bit more complicated than that. X can produce dC and dd. Now, the probability of x given dA, dC, and d can again be is proportional to probability of c, dC, dd given x times probability of x given dA. So this is the same result from the previous slide. It's just that now we have these two data sets separate. Previously, it was one data set. One observation, sorry. And this can be, we also know this from the previous lecture, that probability, dC, dd given x, so you can consider this as two observed variables, is probability of dC given x times probability of d given x times probability of x given dA. You can see how having this structure allows us now to decompose these probabilities. So instead of having one giant distribution here, we can calculating by multiplying more simpler distributions. But things can get even more complicated if you have more hidden variables. Now, say you're interested in probability of C given these two observations, but it doesn't depend directly on these. It has some intermediate unobservable variables that depend on these observations. If you have unobservable variables, then you need to sum over all their values. So you have probability of A given dA times probability of B given dB times probability of C given B and A. In a similar way, if you want to know the probability of a probability of dC and dB, so these two, given this variable, you have these two random variables in between. So you can write it out as probability of dC given C, probability of B given dB, probability of C given A and B, but because these two are unobservable, you have to marginalize over their values. In this case, you have two random variables, A and B. And if you want to calculate the probability of B given dA, you have to marginalize out over A. So you have probability of A given dA times probability of B given A, but you have to marginalize over A. Similar for dB given A, it's probability of dB given B times, so dB given B times B given A, but you have to marginalize over B. So now, if we are back into dialogue modeling, and we want to do belief state tracking for a POMDP, we can apply belief propagation. So observation in turn t and observation in turn t plus 1 is known. We take action. We know these, let's assume we know these probability distributions. Let's forget about reward for a moment. So the probability of this state is proportional to everything that that comes into that state times everything that goes from that state. So everything that goes from that state is the probability of OT plus 1 given ST plus 1. That's the observation probability. And now, because we have this hidden variable here, we need to marginalize out all its values. So then we have the probability of ST plus 1 given AT and ST times the previous probability distribution over states. Okay, now if you're not sleeping, which you may be, does anyone see a problem with this? So you have the probability of states in the current turn is the probability, observation probability times the transition probability, everything what happened before, and summation over all states. If you were to do this in a real dialogue system that can give you reasonable answers in, say, hopefully real time, do you think there would be any problem with this? Yes? Exactly. So this state space is everything that can possibly happen in dialogue. And we have to sum over that in every single turn. So it's intractable. So what can we do? Any ideas? Yes? Yes, and that is one solution, it's called hidden information state system. It only looks at the top states and group everything else together and assume that everything else has a constant shares the same probability. Then this summation can be easier. But is there any other solution? From what we saw before, what made calculation in graphical models simpler? When we went from a big distribution over many variables, how did we make it simpler? Any ideas? How to calculate this distribution in a simpler way? So, what we can do is factorize state into conditionally independent elements. So, because you saw before, say, here, for instance, we only sum over variables values that this state has. So the smaller number of values that a variable can take, the easier it is to calculate. And we don't care how many these random variables we have. So what we can do is decompose the state into elements. Now, instead of having one big state that can have many elements, we can decompose it into 3 states, and each of these 3 states will have a smaller number of elements that it take. So one way of doing this is to decompose it into exactly the things that we want dialog state to be consist of. So we said we want to know the user goal, so that will be one random variable. We want to know what user said, that would be another variable. We want to know the dialog history, that would be the third variable. Now, how are these variables related to each other? Well, dialog history obviously depends on the dialog goal. It also depends on what the user actually said. What the user said depends on what the user has in mind. Now, if we put this back into our POMDP, we get a Bayesian network. So with a big circle, I'm going to denote, for example, that here this action influences all these 3 elements instead of having three errors. This now looks more complicated, but it's actually simpler to calculate the belief over this element. And I'm going to show you how. So you now want to track the belief over goal, action, and dialogue history here. Now, that is the probability of observation. But now observation only depends on what the user said. It doesn't depend on other elements. So this is already simpler. Then you have the probability of user action depending over user goal and action. That is this part here. Now, user goal depends on the action and on the previous goal. But the previous goal is unobservable, so you have to sum over all its values. Then you have dialog history, which depends on the action, but also on the previous dialog history and goal and user action. And you have to sum over all previous goals. And you have the previous belief state, which has user action, and you have to sum over that as well. But this is still problematic because you have potentially large number of user goals and summation over possible histories and user actions. So it's still problematic. So what can we do more? Any ideas? So we can continue decomposing these elements, because we decomposed it into 3 elements, and it's already simpler. If we continue decomposing it, the graph is going to be more complicated, but we will eventually, this summation will be over a small number of values, and it will be easy to calculate. So that is called Bayesian update of dialog state system, originally designed by Blaise Thompson. So it further decomposes the dialog state. It makes tractable belief state update, and it can also learn the shape of these distributions. I'll talk about these two parts. I'll leave this up to you to read more. So, how can we decompose user goal? We saw user goal can be something like user wants cheap Indian place in the center of town. So that would be one goal. Another goal would be user wants cheap Chinese place in the north of town. Instead of having this goal as one random variable, we can actually have separate goal for the cuisine or the type of food that the user wants, and separate goal for area, and another goal for price range, and another goal for stars, and so on. So now, in a very simple system, this takes only 4 values, say northeast, China, west, and so on. Food may take 100 or 200 values, but it's not intractable anymore. So you do the same thing for dialog history, user action, and this graph now becomes very complicated, but we don't care about that anymore, because all we are interested in, for each of these nodes, look at all the observations that we have that go into that node, and for everything, all observations that go out of that node. So in order to do belief tracking, we start on one side, we keep getting probability of X given dA, start on the other end, keep getting probability of D given X. To get the marginal, you simply multiply these. So that was about belief tracking. And now let's talk a little bit about the problem of taking actions. So this is the final problem in dialogue management. And this is actually, Olivier talked about this this morning, but let's now put this in the whole picture. So one example of a belief state, very simple belief state, is this. You have probability that user wants restaurant with 1.0, probability that user wants Thai food with 0.4, Turkish food with 0.3. What to say to the user? Do you say, what kind of food do you want? Do you say, did you say you want Thai food? Or do you say, do you want Thai or Turkish food? In goal-directed dialogue systems that are slot-based, you usually have for each slot these 3 options. Or you can have some general options, such as this Thai restaurant is a good restaurant. So that would be an action which informs about a particular restaurant. Or you can say, can you please repeat, and so on. So you have a variety of actions that you can take in each of these states. And the policy for a particular belief point tells you which action to take. Now, dialogue is a sequential decision process. And as we saw this morning, you want to optimize the sequence of actions. You want the whole dialogue to be intelligent. So you're not only interested in optimizing this action for this particular state, you want to make sure that this follows on this, that it makes sense, the whole dialogue. You do that by observing some rewards. And then you want to find the sequence that gives you the maximum cumulated reward. But what is a reward function? In more general sense, it's a measure of how good the dialogue is. Whether the user is happy or the user is bored. And actually, this is, there hasn't been that much work done into reward engineering. We usually assume there is some reward, but this is definitely an area which needs more research. But now, if we assume we have a reward, what we want to optimize is the Q function. And as we saw this morning, for a given belief state and an action and a particular dialogue policy, if the dialogue is in that particular belief state and we take that action, observe some reward, and then discount it in future, and follow some policy, take the expectation of this, give us a number. This number tells us how good it is to take this action in this belief state. It is a measure of that tells us what impact does this action have on the outcome of the dialogue. So it's look ahead into future, because it looks what happens from this state on until the end of the dialogue. Optimizing this function is equivalent to optimizing the policy pi. So how do we optimize the Q function? Well, ideally, we want to do that in interaction with the environment. But as we saw this morning, standard methods take too many dialogues. So then we need to build a simulated user, which simulates the way people behave. Then we let the dialogue manager interact with this simulated user, and then we optimize the policy. But simulated user is never a very good representation of real user. So that is not ideal. So we want to use sample-efficient methods that would allow us, from a very small number of interaction, to give good results. And such examples include modeling Q function as a Gaussian process or using Kalman filters. And that can allow us to optimize the system in direct interaction with real users. Now, at the end of my talk, I'm going to give you one result, which is actually shows dialogue optimization in direct interaction with real users. So we in Cambridge have an end-to-end spoken dialogue system that operates on tourist information. It can offer you restaurants in Cambridge that can have a particular price range, area, type of food, and you can ask about information about these restaurants. So in order to get real users to talk to the systems, we deployed the system over VoIP, have a US number that you can call. We asked Amazon Mechanical Turk users to call our system. We gave them tasks, say, find a cheap Chinese restaurant in the center of Cambridge. And they called the system. And at the end of the dialogue, the system said, if you were happy with this conversation, press 1, otherwise press 0. And this signal we used as direct reward to the system. So we compared two dialogue strategies. One which is trained on a simulated user using a standard method that took a large number of dialogues, and that is the policy is trained on a simulated user, and this is its success rate. And then we started from completely random policy and measured over time. So after each dialogue, we updated the policy based on the user's satisfaction. And using Gaussian process reinforcement learning, we optimized the policy and we calculated moving average success rate. And you can see that after 1,000 dialogues, it started to level off. So it needed a relatively small number of dialogues to optimize the policy. And this is a very cheap way of optimizing the policy because you don't need anyone to sit down and devise the system. It's fully automatic. Now, this is during learning. So during learning, you need to explore more options. So the system may not always take the best action. But if you take this policy that you get at the end and compare it with the policy that's trained on the simulated user without using exploration, you get 93.5% for simulated trained policy and 96.8% for online trained policy. So it's actually better with almost 50% relative improvement to use the policies trained online. And it actually took at least one PhD student to write the simulated user. So it's not actually that easy to write a good model of user. And one PhD student, so 3 years, and the postdoc afterwards worked on the simulated user. So we think that this is a very good baseline, but it's still better. And this is actually in a research lab condition. So we don't have, we had only one line, people about 100 dialogues a day. So in 2 weeks, you can get a better dialogue system. So that is another problem. These are paid people. So they may not always be very careful in saying, I really got Chinese restaurant with such properties. So the first time we did this experiment, we got very strange results. So it very quickly went up. But then it started going down, up again, down, and it didn't really converge. And we were curious what happened. And then what we did is divided the data into 3 sets: initial training, medium training, and higher level training. And we found out that at the beginning, the probability of user saying bad dialogue when the dialogue was bad. So because we give them task, we know whether the system offered the right restaurant or not. But we are interested in whether they can perceive that. So in the beginning, they were very good in saying this was a bad conversation. But later on, somehow they started saying it's good when it wasn't good. And the reason for this is when, in the beginning of training, the system, the actions are more or less random. So it's very obvious that the system is doing bad recommendation. So then they are good in saying it's bad recommendation. But when you get here, you notice that the system is kind of reasonable. It gave me a Chinese restaurant. It may have not been in the center, but I don't care. And then they started giving their reward function became more noisy. So that sometimes they would say it's good, but it wasn't good. And then this model deals with noisy observation, but doesn't deal very well with noisy reward. So then it went down. And in order to do this, to deal with this in this other experiment that we did, we filter out dialogues that were both objective and subjective reward are the same, and use that for training. And that gave us very good results. But now the question is, how would you do this with real users? So real users are very likely to tell you this dialogue is good when it's good, or this dialogue is bad when it's bad, because they are very interested in the outcome of the system. But what you don't know is what they had in mind. You don't know the task. So how to deal with that, that's an open problem. So to conclude this talk, I talked about statistical dialogue modeling. We talked a lot about state representation, and that we actually require compact state representation. Then we talked about generative versus discriminative dialogue models. And finally, we talked about policy optimization, and that it's designed to maximize the reward, but how actually to define reward, it's still an area of active research. Thank you very much, and if you have any questions, happy to take them.
The interaction is always
So in the online training, we used only if they achieved goal or not, but we also took into account how many turns they needed to take to achieve that goal in order to minimize the time of interaction. You can do all sorts of things. We sometimes use partial reward function as a measure of how good a dialogue is. So we can say the system offered the right venue, but it didn't provide a phone number. So it's still better than not doing anything. So in evaluation, we use both measures, but for training, we usually want the system to give all information. But you can decide. That's an engineering problem. More questions?
So, could you describe a bit your hands-on with Olivier?
So how many? In 30, no? Before? We started, and it lasts until?
I don't know, it's up to you.
Yeah, whatever you prefer. So, a few years ago, there was a problem in dialogue research community that everyone had their own little problems. Somebody is working on, just to give a bit of historical information, someone was working on flights, someone was working on restaurants. So they give numbers for flights, we give numbers for restaurants. How can we compare these two dialogue systems? So in ASR, it's very clear. You have word-error rate, and you can say this on the same, and you have standard data sets that's available to everybody, and people can very easily compare their methods. In dialogue systems, first you have a system which is which combines many different elements, and you put them all together, and plus you don't have a data set or a joint task, so it's almost impossible to compare different methods. So in Pittsburgh, they have this real application where they give information about bus timetable after hours. So the people who are looking for bus, they can call a dialogue system and ask for a bus timetable. So then they said, because we actually have these real people, why don't you guys from the research community build dialogue systems, and we will put for 1 week one dialogue system, for another week another dialogue system, and then we can see which one is better. And that was a great idea. Few research labs took part, and but then it was problematic to say, okay, was our system good because we have very good ASR that we worked 10 years on, or was it good because we have good dialogue management? So then in the second challenge, they decided, let's only focus on one problem. Say, one problem that's easily definable, like dialogue state tracking. You have dialogue, you have the description of states, and you want distribution over these states. So it's a very simple problem. And you don't need people working on ASR for 10 years to build a dialogue system. You can just build this one part of it. And in that way, you can expand research community because people from machine learning or a student who would be interested in this. So that's how Dialogue State Tracking Challenge came about. And in order to make it even more interesting, Cambridge decided to transcribe its own data, which is about restaurants. But the interesting part about this data is that user can change their mind. In the bus information data, the user would only look for a particular bus and that's it. In this data, if there is no Chinese restaurant in the center, you may ask for something else. So it's more interesting from belief tracking point of view. So in order to get you to know this data, I mean, you won't have much time, but hopefully, if you are interested, you can go home and try to build your own dialogue tracker, maybe based on some methods that you heard here. Or there was a special session in SIGDIAL with many interesting methods, so you can read about it. And as a first step to that, you will build a focus dialogue tracker, which we talked about here, and you will compare it to the simple baseline. So that is about practical. There is a handbook which is based on the original handbook from the challenge. So I will give you some time to read the handbook, and then you can start coding. Well, you can take the handbook. It's quite extensive, actually. You will only have to read up to the appendix. It's about 6-7 pages. But this is all based on Matt Henderson's, Blaise Thompson's, and Jason Williams' work. So the original data was transcribed by them, and